Excellent. Thank you for having me here today. My name is Gregor Kaplan, and I am the founding engineer of our Dynamic Augmentation system. And today I'm going to talk to you a bit about that, but also a lot about kind of how I thought about fonts, how I think about fonts, and how that relates to text, or rather how text relates to fonts and how fonts turn text into something we can actually read. Just as an introduction, what is dynamic augmentation? The idea behind dynamic augmentation is to take a font, create a subset out of it, and then to sequentially build up that font over time. And the idea is that you should be supplying to an end user only what they need, and then adding into it over time what they need to render a new view. Talk about me just for a little bit. So I had a font problem, and I'm going to talk to you about how I got to that font problem. And a lot of it has to do with just my background in general. So I am not really a trained engineer, even though I am a senior computer scientist at Adobe. My background's in East Asian studies, and that's really colored my entire perspective on the world and everything that I've done at Adobe. I started in 2000. I got hired as a white box engineer on InDesign, and they had this great job description. This 2000, if you guys don't remember, was sort of the end of the dot-com bubble, and you couldn't find people to work. And they were hiring, you're a jazz musician, great, you can write code. So I saw this ad come up, and it said, we're looking for somebody who speaks Japanese, knows print and prepress, and maybe can write C++ or is willing to learn. And I thought, that's me. That's exactly who I am, and this was the thing that I wanted to do. So I worked on some text validation tools, content validation tools, and automation for InDesign, and then also worked on tools that got ported into Illustrator and also into Acrobat for doing their sort of validation. And so I was really sort of focused on text without necessarily knowing exactly how that functioned. But as we got towards sort of the latter end of the 2000s, my team was transitioning off of desktop. While I was working on porting this code to these other projects, they were working on doing Flash-based applications for internal use in the company. And I had no idea how this worked. I didn't really understand what a server was. I didn't know how you talk to a server. I had no clue how any of this stuff works. So I thought what I'd do is I'm going to make my own Flash app. And what I'm going to do is I'm going to take a month off. I'm going to go work on my own thing so that I don't have any pressure. I don't have any requirements. I can just do my own thing and figure it out. So whenever you want to do something like that, it makes sense to go something to your passion. So one of my passions is cooking. And as a Japanese speaker, and reader really only of cookbooks. I can't really read much of anything else, but I can read cookbooks really well in Japanese. I have a pretty big collection of Japanese cookbooks, and Japanese cookbooks have amazing layout, amazing ways of using pictures and text to explain how you're going to put together a dish. And I had no way of sharing this with my friends. There was no way, like they didn't speak Japanese, it wasn't going to work out for them. So I thought, okay, I'm going to make some sort of application that will allow people to create nice layouts and rendering and to translate those things into multiple languages. And one of the things I learned really early on was that I was going to need fonts on demand, and I'll explain a little bit about how I got to that. So I made this Swift, and this little box here represents basically the size of my Swift. It was about a megabyte and a half with all the logic in it to render and display things, fetch pictures, etc. And it could do some stuff. It could show you recipes. There was an interface where you could translate somebody else's recipe to another recipe. And the idea was that, wow, you had all these recipes. Wouldn't it be cool if you could make your own book? You could print it. And I thought, well, I'll have to get some fonts. So I'm going to embed some fonts. And it's definitely not okay to do that, so don't do that. You're not supposed to do that. But I didn't know any better. And so I did, and I entered like 4 Japanese fonts. And suddenly my little Swift became that. What happened was it went from 1.5 megabytes to 34 megabytes, and I hadn't touched traditional Chinese or simplified Chinese or Korean or any of the Semitic languages. It was just obvious that it was impossibly large. You'd have hundreds and hundreds of megabytes of font data and a 2 megabyte Swift that was actually doing stuff. So what's the problem there? I mean, it's sort of obvious, but really the problem is that they are big, really super extra large big. And to give you a sense of this, I went through everything that's in the ATypI library or in our archives, whether it's public or not, and ran some scripts to pull some stuff out. So your average Western font is somewhere in the order of 500 characters and about 114 kilobytes. Not too bad, but still too big really to use on the web with multiple faces. You line up with half a meg if you were to do 4, and that's a bit much. But when you start looking at East Asian fonts, you're looking at 40 times as many glyphs and 60 times the file size. And that is sort of the fundamental problem with East Asian fonts on the web. It's just a question of bandwidth and size, both on the device and in terms of sending things. So how could you solve that? How could you go about doing that? Well, the first, most obvious thing is to make a subset on demand. And that's a fairly well understood process. You have a view, you collect the Unicode, create a subset. Pretty obvious and straightforward. But the problem with that is if for every view and every page view you have to resubmit the same characters. If you have an A on one page, why do you need an A on another? You've already sent that to the user. So the idea then would become never send the same data twice. Don't try to resend the same thing. Don't do subsets every time, but somehow append into the font as you go. And also never send anything the user didn't ask for. So, an obvious thing would say, well, if you're using, an A, you probably want the alphabet, you're going to take that. But that starts adding things into a font and makes things more inefficient for people. A classic example would be the Q. If you have a Q, it's always followed by a U, and that's always true unless you want to spell Iraq. And then in that case, there is no U, and it would be silly to send that to them. So, here's what I knew. Or didn't know, as the case is. I was really excited when Merritt came up and said that he didn't know anything about fonts, because I thought, hey, that's me. I knew nothing about fonts at all. But I also realized that if you look at George Orwell's Ignorance is Strength, it turns out that that's actually a positive, even though he meant it as a negative. But for me, not knowing things was kind of a good thing. But what is this? We see these things, and they're letters. It's a word, and it's text, and we all know that that's text, right? Well, what is this? How did these things come into existence? How do we go from text into this other text, and why is this text different? And the thing is that under the hood, all of it is really just this. But even then, I still don't know what this is. And so the question is, then, what is this? And what this is, really, is a bunch of numbers. That's all it is. To a computer, it's numbers, just lists and lists of numbers. When you go do a find and replace, it's looking for numbers. It's not actually looking for letters. There are no letters. It's just numbers. They're just Unicode. And so the question is, how do these numbers become something that we can all understand and read? And so how that happens, how does it translation into this? It all happens through mapping. And through the magic of the CMAP. The CMAP is a character map, and it's a table really that is the entry point into a font. It's the thing that can get you to everything else that is there. And sort of what you do is you take Unicode, and I like to think of a font as something that does stuff. In actuality, something has to parse the font and then do stuff with it, but I think of it internally as something that does something. So you take your Unicode, or some other encoding format, you pass it through the CMAP, and it spits you out a glyph ID, and that glyph ID is an internal ID within the font. So if you took the capital W, it's U57, passed through the CMAP, and this particular font, Acumen Pro Condensed Light, it lands up being glyph ID 24. And in fact, you can apply this process to every other glyph that's in there and spit out the glyph IDs. And the thing about glyph IDs is they're really internal references to things. And they're not necessarily in any kind of logical order. If you look at say the A, it does in fact have a lowercase a, it does in fact have a lower glyph ID than H, comes before that. But then you get down to the question mark that's at the bottom. And the question mark here has a glyph ID of 450, even though its Unicode value is much, much lower. And the reason that is that there's actually no connection between what the Unicode values are and what the glyph ID values are. They're sort of arbitrary, and they can be anything you want. When you start looking at other fonts, then it starts becoming completely different. And you'll notice here there's actually just no relationship, that you can't take glyph IDs in one font and apply them to another and hope to come up with anything other than garbage. So of course, all of you can read this slide and know what this says, because this is what a computer sees. But what this actually is, of course, is text. And we use that CMAP to then reference everything else that's in the font, how characters relate to each other, how to render them, when you're going to come up with a substitution or an alternate to something. So when we look at this sort of in review, there's this stuff called text, which is really just numbers. And then we have fonts. And really, no one really knows how they kind of work. At least I didn't know how they worked, because within a font, there's really just more numbers. And they're all glyph IDs. And these glyph IDs are what we use then to render text. So, okay, well, what's subsetting? So just some preliminaries. If we can use Unicode or use a font CMAP to map Unicode into glyph ID, glyph IDs kind of serve like a primary key. You can think of a glyph ID like it's a primary key for other information. And within a font, you have tables. And you have some tables that apply globally to the entire font. that you really don't need to subset because they are global. And then you have glyph-specific tables. So examples of font-wide tables would be like the baseline table that will tell you where you're going to basically align certain characters or certain glyphs, particularly for a script. So an East Asian font may center align, and a Western font may bottom align. Maximum profile table that will tell you, how many points could you potentially need to store in memory. And it'll tell you, okay, well, I need to allocate this much memory for every glyph so I can be safe. And they're just things that apply to everything within the font. And that might also tell you how many glyphs there are in the font. And then you have glyph-specific tables, and this is where things are sort of interesting. You have the CFF or the glyph table, and that's what you use to actually draw the character. The glyph positioning table, the GPOS table, tells you how to kern. It tells you how to place diacritic marks. The G subtable is glyph substitution table, sort of obviously. That's where you're going to find your ligatures and your fractions and your ultimate forms, stylistic sets, etc. This is a way of taking one character and turning it into another. And when you think about all of these things in combination, what you realize is a font is really a static relational database. And by static, I mean the font itself is not changing. But what it is, or what it can serve as, is a relational database. That's how you relate all of this information together. So when we look at what font subsetting is, it just basically reduces the font down to the glyphs that are required for requested content. Or you could say, well, here is the definition for French, and I'm going to have these characters for French. So it doesn't have to be a document. It could just be a set of characters that you predefined. Again, usually it's based on the required text. And maybe you can also specify, I don't care about these OpenType features, but I do care about these other OpenType features. So if you have them, please supply them to me. And that's really dependent on the subsetting engine itself. Now, there's some rules about glyph IDs. First off, there was the no tofu reference earlier. That's glyph ID 0, and that's in every font, and that has to be there. It just says, hey, I don't know what the hell you're doing. Render this box. But after that, they have to go up through n-1. So if you have 100 glyphs, counting the not def glyph, the highest glyph ID is going to be 99. So if you look at an example, in this case in Magneta by Positype, these are the glyph IDs for FIST. Now, here also, though, there is a ligature. And so this ligature is glyph ID 314. And what we see as 3 characters, we see FIST, is actually only rendering 3 characters. It renders an FI, an S, and a T. So even though to our mind and our way of thinking, we're seeing 4 characters, there's really only 3 there. But if you rearrange these letters, you have to also take into account that you could have SIFT, in which case you need the FT ligature there as well. So when you made a subset out of these 4 requested Unicode characters, you land up with a subset that looks something like this. 0 obviously is not defined, and we go up through 6. Now, the GSub table is super interesting, and I kind of love both the GSub and the GPOS table. They're really elegant and beautiful. And if you wanted to look at a rule for how you would do a substitution, it looks something like this. You have F followed by I, replace it with FI. But because everything in a font is actually just numbers, really what it says is 45 followed by 48, replace it with 314. Or in our subset, 1 followed by 2, lines up with 5. And that's all cool, but it's all just numbers. And if we were to go then to a secondary subset, say we wanted to spell flip, and we're going to do a subset for that, again, it's got an FL ligature, so we're going to have that as glyph ID 5, and we're in 1, 2, 3, 4. Pretty straightforward, but you might notice that there's a problem here. If we go and look at these 2 different subsets, there's a conflict. In one case, S is mapped to 3, and in another case, L is mapped to 3. And this is a problem because there's actually no syntactic meaning within a font for what glyph IDs are. They are meaningless. They are simply numbers, and the font doesn't know what they are. So you couldn't really go and combine these 2 subsets because the glyph IDs are in conflict with each other. There's no way to recreate the relationship, say, between an S and an L because they've both been mapped to the same glyph ID, and that is sort of the fundamental problem with how you would go about doing some kind of dynamic augmentation. So what is dynamic augmentation? Essentially, it's a means of supplying data to the font and rebuilding it piecemeal in any order at all. It doesn't matter which order you're taking these values. You just need to put them in and make sure they get to the right place. And the key to all of this is knowing the state of the client font. If you know the state of the subset, if you know how all of these things have been remapped, you can know how to alter them and to create a set of instructions that will allow you to update it. So if we started with FIST, with that subset we started there, and I say, okay, I'm going to need LP and also this, any OpenType features you have, which happens to, in this case, include a ligature, the server's going to respond and say something like, hey, add in these 3 with these values, and go ahead and also update the S, the T, the FI, and the FT ligatures, and you land up with a subset that is complete. So to look at these sort of as instructions or as a process, we start with a page that has FIST, we request these Unicode values plus their OpenType features, and we produce this subset. Then the page updates to have flip in it. We say, okay, we need these two Unicode values, and here's my client state, and it spits back these new values and all of the information about those characters, and also how to update the existing ones. And then we land up with a subset that looks like this. So we're going to look at a couple of practical applications of this, or examples of this rather, that are based on HTML and JavaScript. I wrote basically our backend engine, and the process wrote the spec internally to Adobe. And then Bram Stein, my partner, wrote all the JavaScript for this, which is really also beautiful in and of itself and probably its own talk. We're going to look at a simple subset, that's a simple subset, starting with subset and then doing some augmentation in it. We'll get a sense of how long this takes and what the user experience is like. And then we're going to look at the worst case scenario. And the worst case scenario is typing, right? So you're getting arbitrary glyphs coming in one at a time, pop, 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 pop. How to respond to these and what does that sort of process look like and how does it feel to an end user. So we're going to look at this font, which is Roomin by Morisawa. And what I'm doing here is I start with a base font. I'm going to copy some text off the Typekit splash page and paste it in. And there you go. It pops in. You'll see a little bit of a sort of flash. Some of the characters aren't there yet. And then you'll see them come in. So if you just watch for some very thin characters, and then boom, they've been replaced. And what's interesting here actually is on the timeline. Before I dive into the timeline, this particular font in its raw form is 9.8 megabytes. And using WAF2 compression at its highest compression ratio, it'll get down to 7.4, which is a nice savings, but it's still not particularly usable on the web. A 7.4 megabyte font is just too large. If we look at the timeline and we look at what was getting delivered, we started here. This was the initial subset. It was a 273 kilobyte subset. When we pasted in this text, we ended up getting back a response that was 142 kilobytes. There's some overhead in there, and some more amount of data was added into the font, but if you had to do two subsets, you'd probably be looking at 300K for the second subset. And when you do the third subset addition or third augmentation, it's basically 140K more, but again, because this is accretive, and you're adding into this font locally, if you'd had to do three subsets, you would have been looking at probably 270, 300, 330, you'd have been pushing a megabyte right there, and instead we're able to deliver this in a little over 500K. This is a much more efficient system for getting stuff into the browser. The last movie or play we're going to look at is typing. And the thing to really look for in this is you'll see some of the text come in very thin, and then it'll get replaced by a nice fat rounded font. In this case, Heisei Kakugo by Adobe. And it's me typing. Hopefully I didn't screw anything up. Well, let's take a look. There we go. It is actually typing now. So if you're watching these glyphs come in, like everything right now is already there. They're already in the initial subset. And everything's nice and fat and rounded and happy and been eating a lot, as I have been doing for the last few days. But you'll notice in a second here, you'll see some stuff kind of flash in a very thin, very thin line. There it is, boom. And that was the time that it took to update this thing. So even though there's a bit of a flash, if you were a clever JavaScript developer, you could probably hide this text as it was coming in, not display it until the update came through. I'm not a clever JavaScript developer, so in fact, I'm not a JavaScript developer at all. But you can see that there's a little bit of a lag. But what this enabled you to do was instead of having to use a 9.8 or 7.4 megabyte, depending on if you had waffleized it, to use a very, very large font very quickly and very efficiently, something that would work on a cell phone, on a mobile device, or even in a browser. So I have some sort of general thoughts to bring us to a close. The main thing for this, and our main goal for this, pardon me. Let me get this last slide. Hopefully it won't transition out on me again. I wanted to provide a mechanism where people could use large fonts. Again, my background, my passion is for East Asian languages. And I really wanted to contribute back to people who've brought so much richness to my own life. And I wanted there to be a way that people could use web fonts for these languages. It turns out this is also super useful for Western fonts. But it can be a little bit of overkill. First off, there's limited browser support. You have to be dealing with IE9 plus. Some of the older browsers don't function quite as well. It's a little bit of memory constrained. And so Sometimes it might be better to use a WAF for something like a Western font, or if you already know what your subset is going to be, you can start with something that's much smaller. But in terms of being able to provide something like an RSS feed or articles that are dynamic or just general dynamic content, especially for East Asian languages, this is the mechanism that we came up with to supply that. Thank you very much, and I'm glad that I had a chance to talk to you guys.
Thank you. Again, we have time for one question. Does anybody have a question? Oh, great.
When do you imagine that this incredibly futuristic technology will be available to the general public?
This incredibly futuristic technology will be available to the general public about 15 months ago. So it has been there since June, I believe, 15th of last year. We started the project, or I started the project in early 2008. Started writing code in early 2009. It took about 2 or 3 years to get it to the point that we're able to really start using it.
Great, thank you.